F4 slot. So F4 slot is Wednesday 10, Thursday 9, and Friday 11 to 1, right? So this is 9 to 10, 10 to 11. So these are the 4 classes we'll have every week, and all the lectures for these 4 classes, notes, everything will be available in your Teams files. Okay. So let us start with the class. So linear algebra. Okay. So linear algebra basically is study of vectors and matrices for us. Okay. Vectors and matrices, and how we will use vectors and matrices, how we will apply them in AI MLDA. That is what we really want to explore. So many of you would have done first course in linear algebra, and you would have talked about vector spaces on real fields and complex fields and things like that, right? In your maths 2 course, you talk those things very extensively. So we'll not go into those, and we'll directly start with what are the vectors and how we can use vectors to represent few things, and few operations on the vectors and matrices. Okay, so that's what we'll start with, and we'll immediately start seeing applications of those things in AI ML. Okay, so by introducing few things in first couple of classes, the first thing that we'll look at is k-means clustering algorithm, and what type of what are the concepts that are used from linear algebra in k-means clustering algorithm. Okay, so that is the objective of the talks. So today I'm starting with few concepts, and tomorrow also I'll do a few concepts from vectors and matrices. Initially for a couple of weeks, just to bring everybody on the same platform. You may feel that things are very easy, but I can assure you after first couple of weeks, we'll really pick up things, and we'll really start learning involved concepts from matrices and other important applications. Okay, so the typical things that we want to look at, okay, are basically the least squares problems. So I'll just write down as LS problems. So least squares problems are something that we really are interested in looking at. So there are various types of least squares problems. So the least squares problems that we will look at is simple straightforward least squares problem, non-linear least squares problem. Okay, so linear, non-linear least squares problems, and we will look at something which is called as constrained least squares problem, then multi-objective least squares problem. So these are the different types of least square problems that we want to look at. And these least squares problems have applications in various things. The first important application is data fitting. Okay, so these least squares problems have applications in various fields. The application that we are interested in is that of data fitting, or something which is equivalently known as regression problems that you might have seen. So these are the things that we are really interested in. Then what we are really interested in is matrix decompositions. Okay, so we will use various matrix decompositions in this course, and these matrix decompositions we will learn, and the applications of these matrix decompositions we'll try to learn. So the matrix decompositions that we will learn will be QR decomposition, singular value decomposition. Okay, so QR decomposition we'll learn because QR decomposition is actually really very helpful. QR decomposition is very helpful in obtaining the solution of least squares problems. Okay, so why is QR decomposition important? We will try to solve least squares problem to QR decomposition. Then there will be something which is called as singular value decomposition. The singular value decomposition is extremely important decomposition, and I think everybody knows what is singular value decomposition. It has a lot of applications in real life. One of the most important applications is PCA, principal component analysis. So we'll learn about principal component analysis, and we will see how SVD and PCA are related. that is important thing that we will look at. Then another decompositions that we will like to learn are low rank approximations. Okay, the decompositions that we will like to learn are low rank approximations. So these low rank approximations are very important. These low rank approximations throw light on many real life applications, and one of the important applications for low rank approximations that we want to look at is in neural networks. Okay, application in neural networks. on reducing the number of parameters that we train. Okay, reducing number of parameters in training. Okay, so we will try to see what is the architecture of neural network, like fully connected neural network that we are talking about, and reducing number of parameters in training. Okay, without compromising obviously on the generalization of the neural network. So that is something that we will like to. That is something that we'll like to look at. So low rank approximations are really very important. Another application of low rank approximations, another application. So other problem which is very similar to low rank approximation is low rank completion, low rank matrix completion problem. Okay, low rank matrix completion problem. So these are the type of problems, low rank matrix completion problems, which are very useful in collaborative filtering. Okay, so for example, Netflix had that open challenge, right? You have to sort of predict in real time, like the suggestions for you to view based on the ratings that you provide in the past. So ratings, so the users can be along the rows, and the database, like all the movies, can be along the columns, and each user gives some rating to each or some of the database entries, right? So suppose I like Harry Potter movies, so I give high rankings to Harry Potter movie, and so on and so forth, right? So there are some entries in this very huge matrix which are given filled, and based on that, can you complete all the entries of the matrix, which is like saying that you will be suggesting uh, recommendations for every user for every database, right? So that is like low rank completion. So why low rank and why matrix completion really helps. So these are the type of problems that we will really like to focus on. Okay, and then if there is time, we will talk of multilinear. Okay, multilinear algebra, or tensors. Okay, so all these things that we are talking of, we will like to generalize to tensors and see how we can do low rank approximations in tensors, or how we can do low rank tensor completion problems, and what are their applications in AI and LDL. That is something that we will like to know. So the general idea will be, there are three important topics that we will alert, like mainly two important topics in this course. One is least squares problem, and one is matrix decompositions. Though I have kind of segregated these two problems separately, least squares and matrix decompositions, I will like sort of be mixed in teaching. Okay, because there are various things that I will like to introduce before, and then we'll start talking of these problems. So for example, we'll talk of solving system of linear equations first, then only we can talk of least squares problem, and we will talk of condition numbers of matrices, because they are very important. So in between, I will speak of many things. So once I speak condition number, I will almost introduce what is singular value decomposition. So the concepts, the way I will teach, they will be mixed, but these are the two important things that we really want to do: least squares problems and matrix decompositions. And the way books are, the first book, the Stephen Boyd book, actually mainly focuses on least squares problem. So the Stephen Boyd books mainly talks of this part, and Gilbert Strang book mainly talks of this part. Okay, so roughly the books are talking of these things, and I'm going to mix both the things together. Okay, so that is how the course is going to be. So this is what we will do, and every concept that we will introduce in this course, we'll try to come up with some example from AI MLDL, where and why these things are. Okay, so that is the objective. So this is the rough idea, rough sketch of what we are going to do. These are the problems that we are going to solve. So at this point, do you have any particular problem or any particular application of linear algebra in your mind that you want to be covered in this particular course? You are looking forward to learning that, but I have not covered here. So that's what I want to know. Am, am I audible? I think Ashwin is saying something. Am I not audible to people?
Audible, sir.
Okay, fine. Okay, fine. So is there anything that you want to learn in this particular course, you want to be introduced in this course, that I have not said here? If there is time and we can incorporate, we will definitely try to include that. Okay, so let's move to the introduction part. I'll start introducing vectors. Okay, so what are vectors? So everybody know vectors is like arrangement of numbers in an array. So typically we will denote the vectors in this course as column vectors. Okay, so typically for us vectors will be always column. So that is the notation we will use throughout the class. So whenever I say x, y are vectors, they are column vectors. They are taking entries from real numbers. So this R will denote set of real numbers. Okay. So for those who know, who are introduced to more advanced concept, then you know that this actually is a field. Okay, it has certain algebraic properties. So this is a field of real numbers, and I will denote an n here. So this n denotes how many components are there. Okay, how many components or how many entries. Many components or entries in a vector. Okay, so typically x belongs to Rn. I will also sometimes say x is an n vector. Okay, x is an n vector. N vector meaning there are n entries in a vector. Okay, so x is generally x1 up to xn. So this belongs to Rn, means that x1, x2, xn, all of them are real number. How many entries in the list? N entries in the list. And this is what the vector really looks like. And the first and simplest operation on a vector is transpose. So the first operation on a vector that we should know is transpose. So x is in Rn is basically same as saying x is in Rn cross 1. Okay, so that means that there are n rows and one column. Okay, so when I use this, how many rows and how many columns. So later on, I will generalize this symbol to matrices. When I'll say Rm cross n, that means that I am talking of a matrix of size m by n with entries coming from real numbers. What is m? M is the number of rows and n is the number of columns. That's the notation I use for matrices. So basically Rn means this. And what is the transpose? Transpose means I am just writing this column vector as a row vector. So x transpose is basically now a row, x1, x2 up to xn. So this belongs to R1 by n. So there is one row and n columns now. So this is first column, this is second column, this is nth column. Right? So this is just the rearrangement. Rather than writing it as a column vector, now I am writing it as a row vector, right? So that's the first operation, transpose operation that we see, and this is something that is basic. I hope everybody knows. So these vectors, where does these vectors really come from? Okay, so some of the examples of the vectors. So what are the examples of the vectors? So few examples. The first example is color. Okay. So what is the color vector? So color vector is a 3 vector. Okay, what is the color vector? It's a 3 vector. Vinod, you are not able to see what I am writing. I am sharing the screen. Is the screen not visible to you, Vinod?
That's what I was trying to see, whether it's available in the whiteboard.
I am
I'm not.
sharing my screen, and I think you are able to see. I have logged in through 2 devices. I can see the screen on the second device that I have shared. I am
Uh,
writing real time and I am sharing the screen. If you are using, if you are using yeah, I don't know if you're using mobile, then I don't know. But I think screen is visible. You can try rejoining. That's right.
okay.
So color is a 3 vector, and what is the 3 vector representing? Okay, so each entry, each entry is between 0 and 1. Okay, between 0 and 1. 0 and 1. Okay, so any real number between 0 and 1, each entry. And this 3 vector, so x1, x2, x3. Okay, so this x1 corresponds to R, this corresponds to G, and this corresponds to B. Okay, so the intensity in each of the channels RGB. Okay, so RGB, red, green, and blue. So those who know a little bit of image processing, so these are the 3 basic colors, red, green, and blue. And any color that you see, you can any color that you can see, that is combination of these three colors, the intensity values. Okay, so for example, if I have the vector 1 0 0, then this 1 0 0 actually represents the red color. Okay, if you have 0 1 0, then it represents green color, and so on so forth. So suppose if I have this 1 1 0, okay, so I'm mixing red and green, then what do I get? I get yellow. Okay, so the intensity is this. Then that's how the color vector is represented. Okay, so this is a vector. X is a vector in R3, color vector. So that is one application of vector. That is where you get these color vectors. Okay. The other example of vectors that you will get in real life is generally time series. Okay, so time series realizations. Okay, so time series or signal. So signal processing guys like to call it a signal. Data science guys like to call it a time series. So this is a time series or a signal. So these are values of some quantity at different times, right? So values of quantities. So typically n values of any quantity at n different time instance, right? N different time instance. So that is a vector. So where do you, so this is x, which is a n vector. So x1, x2 up to xn. This is an n vector. So this n vector actually values of quantity. Say for example, a stock. In a stock market, n is equal to 31. So in the month of August, this is August month. In the month of August, what was the closing value of a particular stock? Okay, so on first day, second day, third day, nth day of August, right? 31st day of August. So these are the values. You put them in a vector, that becomes your time series, and each element, each entry of the vector has a timestamp: first day, second day, third day, so on and so forth. So that's one more vector. That's one more vector that you get. That is the instance of vector. Other thing is the amount of rainfall falling in KGP in the month of August, right? First day of August, second day of August. You will write the rainfall falling. That x1 is the x1 mm on 1st August, x2 mm on 2nd August, and so on and so forth, right? So that is something that you can use vectors for. Another interesting thing is images. Okay, grayscale image. So black and white images that you see. So if you see a image, any grayscale image, basically that grayscale image, you can divide it into the pixels, right? So suppose m pixels here and n pixels here. Then basically a grayscale image is a vector of a matrix of the size m cross n. So suppose these are the pixels. Then you will look at the intensity value at each pixel, right? So you will look at the intensity value here. So whatever is the intensity value, that will decide the intensity of grayness that you will store in that pixel, right? And based on those all such intensity value, you get a black and white image, right? So that's how a grayscale image is stored. So this m by n, m cross n, okay, so those grayscale images, m cross n matrices, so you can write them as a vector r m n, okay, r m n, m times n, okay, so it will be really a very long vector. And how will I get such a long vector? First, I will store all the entries in the first column. So I will write down all the entries first. Okay, so that's what I'll write down. So this is an interesting operation. This operation is called as vectorization. So this first n entries, so these are first column entries. Okay, first column entries in this. Then what will I do? I will look at the second column entries. So the second column entries, grayscale entries. So I will look at this. So these are the next n values. Okay, second column. So how many values are these? These are n in number. N in number. How many are these? These are n in numbers. So how many such things I'll get? I'll get m such things, and total number of entries in the vector will be Rn. So what are the typical values stored here? The typical values stored here are the intensity values. So intensity values always lie between 0 and 1, right? So intensity values lie between 0 and 1. And I don't know, I'm not sure of convention. I think 0 means black and 1 means white, or the other way around, okay? It's based on your convention. So these are the intensity values. They will always belong to closed interval 0 1. So each entry here is an entry in closed interval 0, 1. It will correspond to intensity of certain pixel. So these will be the intensities here in these pixels. That is the intensity values. Then the intensity values coming in the second column of the pixel, so on and so forth, up to the mth column of the pixel, right? So this particular operation of going from m by n matrix to a mn size vector is called as vectorization operation. Okay, so this operation is called as vectorization operation. I think we will get a chance to look at this vectorization operation later on. Okay, so that is something that is really very important. We are doing vectorization. So that's how you can store. That's how you can store an image of m by n. So one of the most important grayscale image data sets that we will look in this particular course is MNIST handwritten data sets. Okay, so you will see these MNIST handwritten data sets, and we will do a lot of operations on these MNIST handwritten data sets. I think all the examples that I'm going to cover in this class, all the examples related to AI, ML, whatever examples, everywhere you can implement those things on MNIST data set. So I think you will have one video tutorial given by your TA very soon about how to download this MNIST data set, how to convert these images into vectors, how do you store those images, and what are the operations that you will do subsequently on this MNIST data set, right? So now the first thing that you can do when I talk of k-means clustering is you can apply k-means clustering on these MNIST data sets. So what is MNIST data set? It's a I think 27 by 27 images. Okay, so 27 by 27 pixels, and in this image the digits are written. Okay, so the image is of handwritten digits. Okay, so people have been asked to write digits, so 6, 5, 10, and there are about 70,000 images, 80,000 images of handwritten digits, and obviously you want to sort of classify them or put them in different clusters. So like all sixes in the same cluster, all fives in same cluster, sevens in one cluster. So these are handwritten data sets. So whatever algorithm you design, the algorithm has to learn to put them into different data sets. Okay, so that's what we are going to do. So on the MNIST data set, you will use this MNIST data set extensively. So this is something that you will have to look at. So it will be a grayscale image data set. So that grayscale image, the first thing that you will do many times is to convert this grayscale image into a vector, tall vector. So here in this case, we will convert it into a 784 tall vector. Okay, so that's what you will do. So this is again something that that is important. Okay, so grayscale images. So the next example of vectors you can think of is word count and histogram. Okay, so word count and histograms. So what generally happens in NLP, natural language processing, there is a word dictionary given to you. Okay, so there is a word dictionary given to you, dictionary of n words. Okay, dictionary of n words. So you form a n vector. You form a n vector from the dictionary. So whatever the words are in the dictionary, they correspond to these rows. Okay. So like the dictionary contains 10 words, then the 10 words will come along the rows. And in a given text, you will count how many number of times the words in the dictionary come. So the first word in the dictionary, second word in the dictionary, nth word in the dictionary, you count how many number of times these words come. So the first word may come 5 times, second word may come 0 times, third word may come 1 time only, and so on and so forth. This word may come 10 times, right? So you'll have a vector of non-negative integers specifically, and you will be counting the number of words. You will be counting the number of words. So this is a word count vector. Okay, so this is a word count vector. So this vector is word count vector, and this word count vector is something that is very important. We'll use these type of vectors in examples where we will be talking of NLP applications. Okay, so using these words, we'll try to see like if two documents are similar or not. So in order that two documents are similar, these word count vectors should be similar to each other. So we'll try to define what is similarity of the two vectors. So similarity will be decided based on the distance and things like that, right? So based on all these type of things, you will try to come up with these word count vectors. Then those word count vectors will try to find similarity. We'll define what is similarity, but that's what we want to do. So similarity can be defined in something which is called as norm. So that is the linear algebra concept of norm or distance of the vectors we'll learn, and immediately we'll try to see how this can be used in k-means clustering. So that is the objective. That is what we really want to do as our first application of linear algebra concepts. So this is a word count vector. Okay, so this word count vector you can see. So there are various things. So one more thing that typically we will always have is features. Okay, features vector or attributes vector. So there will be some features related to observation. Those features will enlist, so it can have k features. So it will be a k vector with k features. First feature value, second feature value. So you are observing k feature and you are writing down those values. So this is first feature value, k feature value, and so on and so forth. Okay, so these are the n values of the feature, k values of the feature in a k feature vector. Okay, you will be looking at. So it will be a vector in rk and so on and so forth. So that is something that is really very important. So these are various types of vectors. These are various types of examples of vectors that we will encounter as applications. So I'm not like typically giving other examples that you get in linear algebra course. Okay, so these are the examples. These are the type of vectors that we'll be working with, and now let us see few operations on vectors. Okay, so is this part clear so far? Like any doubt so far in what we have done? Okay, so we'll go to the next part, operations on vectors. So there are two important operations on vectors. First is vector addition. So the first operation is vector addition. So what do we do? It's very trivial, very intuitive. Suppose x and y are two vectors in Rn. So now you need vectors of the same sizes for addition. Okay, so x and y are two vectors in Rn. Then x plus y is defined component-wise addition. Okay, component-wise or entry-wise addition. Correct. So what do? You add two vectors. So x1 up to xn is the first entry, first vector. Y1 up to yn is second vector. You do vector component wise addition, x1 plus y1, xn plus y. Correct. So that is what you do, entry wise vector addition. And there are certain properties of this vector addition. What are the properties? The properties are trivial, so I'll just write it down and you see, you can convince yourself of those properties. So the first property is commutativity. So vector addition is commutative. So what is commutative? Commutative means you add x plus y in any order, x plus y or y plus x, the result is same. The second property is associativity. So vector addition is associative. What does that mean? The order in which you add does not matter. So you add, if you want to add three vectors x, y, and z, whether you add x and y first and then add z to it, or you add y and z first and then add x to it, it doesn't matter. The order is same. Okay, so that is something that is can be noted. Then there exists a zero vector. Okay, there exists a zero vector. So what is this zero vector? Zero vector I will denote by a zero. Okay, a zero vector. So zero vector is basically all zero entries, okay, such that x plus 0 is equal to 0 plus x is equal to x. And this zero vector is called as additive identity, okay, additive identity. And there is one more property of this. The property is saying that there exists a vector b, there exists a vector b in Rn such that a plus b is equal to b plus a is equal to 0, and this vector b is called as additive inverse. And it's trivial to see what is this vector b, right? So if you have a vector a which is a1 a2 up to an, there is a vector, okay, so b, so I'll just write down b such that x plus b is equal to b plus x is equal to 0. Okay, I have not defined a. So if you have a vector x1, x2 up to xn, then clearly what should be b? minus of x1 minus of x2 up to minus of xn, right? Then you add these and you get the zero additive identity. So right now I have used the article A here, like there exists a additive identity, there exists a additive inverse, but in reality you can actually prove that there is a unique additive identity and unique additive inverse. There is no it's the, okay? So in standard linear algebra courses, you can see people will prove these things, like prove that additive identity is unique, prove that additive inverse is unique, and so on. So this is about vector addition. So this operation is the addition of vectors. And what are the examples of addition of vectors? Now you can see one immediate application of addition operation is that word count. So suppose there are two documents that you are looking at. So for example, one document is divided into two paragraphs. Okay, so one paragraph word count is first vector, second paragraph word count is second vector. You add these two vectors and then you get word counts in the entire document. Right? So you can do things parallelly, like count the words parallelly between the two paragraphs and then put them together by addition, and you get like word count vector for the entire document. That's straightforward application of addition of vectors. Okay. Then another interesting operation is scalar multiplication. Another important operation on vectors is that of scalar multiplication. So what is the scalar multiplication operation? So you get a vector x in Rn, and you get a scalar alpha is in R. Okay, you get a scalar alpha in R. And what is the operation? Typically alpha dot x, but we will skip the dot, alpha x. So this vector belongs to Rn. And how do you define this alpha x? Alpha times x1, alpha times x2, alpha times xn, right? So that's how you define. That means that you multiply the scalar alpha to every component, of the vector. So again, component wise multiplication of real numbers. That's what this is. So this is scalar multiplication. So scalar multiplication, again, it's easy. So properties of scalar multiplication, typically properties of scalar multiplication very similar. So for alpha, beta, gamma scalars and x, y vectors in Rn, you can see alpha plus beta x will be equal to alpha x plus beta x, right? Then second property is alpha into x plus y. You will see it is alpha x plus alpha y. The third property that you will see is alpha beta into x is basically alpha into beta x, right? So these are different properties of scalar multiplication that you can observe. Another important property is you multiply minus 1 to the vector x, we'll write it as minus x. So this is actually the additive inverse, okay? Additive inverse of the vector x in R, correct? So this is the additive inverse of x in the vector R. So this is the scalar multiplication operation. And with this scalar multiplication operation, there are again lots of examples. So one example of scalar multiplication operation I can give is one example I can give is that suppose x in Rn is an audio signal. It's an audio signal, okay? So this is an audio signal. So it's a time series, right? So at n different time instances, I have recorded the intensity of the sound. So that's the audio signal I'm looking at. If I multiply it by alpha, in R plus, okay, so R plus meaning some positive constant. So if I multiply it by alpha, then what is alpha x? Actually, alpha x is the modulation of this audio signal. That means that if alpha is between 0 to 1, then I am listening to the quieter sound. If alpha is greater than 1, then I am listening to a louder sound of the same audio signal. So the amplitude, so to speak, is being changed of the audio signal, and alpha x will decide the intensity with which you listen to the sound, right? Same as, turning the volume low or up. That's what you're doing. You have an audio signal and you turn the audio signal like you turn the knob, low volume, high volume, or so on and so forth. So that alpha is basically the scalar multiple that you're looking at, and that scalar multiple will decide how much is the intensity modulation happening in that audio signal. So that is something that is really very important. So this is one example of scalar multiplication. Typically what happens, the scalar multiplication actually scales the vectors, right? So in R2, R3, where geometry is visible in vectors. So in R2, what happens? In R2, every point. So this is an ordered pair x1, x2. So this is a vector. So typically in R2, how do we denote the vectors? We denote the vectors with an arrow. But it is not necessary to draw an arrow also. Okay, so geometrically, this is what a vector is. Our importance is this coordinates, right? X1, x2, that's how we denote. And then I think all of you understand what is vector addition. So suppose this is x1, x2, and this is y1, y2. Then what do? You do like all of you did parallelogram law. So you complete the parallelogram, and after completing the parallelogram, what do you see? The diagonal. So the diagonal here that you can draw. So this is actually x1 plus x1 plus y1, x2 plus y, right? So this is the vector x plus y, the diagonal of this parallelogram, right? So this is the geometry that we all have done. What does scalar multiplication really mean geometrically? So suppose this is the vector x. Suppose this is the vector x that you have in R2. Then what does scalar multiplication mean? The scalar multiplication means that you still remain on the line. Okay, so what is the line? The line is this line on which the vector x is lying, right? So on this line, when do you multiply alpha x? Suppose alpha is positive, alpha positive, alpha greater than 1, then what you are doing, you are actually elongating the vector, right? So this is your alpha x when alpha is positive and greater than 1. When alpha is between 0 and 1, what are you doing? When alpha is between 0 and 1, you are actually shrinking the vector, but you are remaining on the same side, right? So this is alpha x for 0 less than alpha less than 1. When alpha is equal to 1, x remains x. When alpha is equal to 0, you are at 0, right? When alpha is negative number and greater than 1, then what is minus of x? Minus of x is this. This is the additive identity. So this is minus of x, additive identity. When alpha is greater than, less than minus 1, so what happens? You are here. So this is like your minus, so alpha x when alpha is less than minus 1, and when minus 1 less than alpha less than 1, you are shrinking but in the opposite direction. So this is where you are going. So this is like your minus alpha x, right? So this is what geometrically you are doing by scalar multiplication. You are remaining on the straight line. By negative sign you change the direction, and by alpha greater than 1 less than 1 you are shrinking or enlarging the vector. That's what you are able to do. So these are the two geometrical interpretations of addition and scalar multiplication. And I think time is up, so we can stop here. Tomorrow we'll start with the next concept of linear combination, and we'll see what the linear combinations really mean. So any doubt about what we have done today so far? Okay, then we'll stop here today. We'll meet tomorrow again at 9 o'clock. Thank you.
Sir,
Yes.
sir, I
So
have a question.
Yes.